Hi guys. I thought I'd run through the state monad example again today, and what I want to do is actually run through a sample evaluation of the foo function that we wrote today. But I'm just going to reintroduce everything from scratch, and uh, hopefully you'll be able to follow along. So this time around, I've decided that I'm going to make the state monad polymorphic. So I'm going to use this definition here, data S parameterized on the state and the return value A, and I'm just going to use the Haskell record syntax, S of run S, S to A comma S. I've decided to shorten state to just capital S. Right, okay. So, something you should know is that run S has the following type. It takes an S of A, and then takes an S, and then returns an A of S. That's going to be important later on, okay? It's a way of just unwrapping this data constructor here. All right, so this afternoon I ran through what the monad instance would be for this, and I know it was a bit complicated, and it really does just take a lot of practice to get familiar with how this actually works. But I'm going to run through writing it again, okay? So we'll start off with instance monad S, where you'll see that I've partially applied this parameter lowercase s because the thing that goes in a monad instance must have kind star to star. Alright, so we know from monads that return has to have the type A to SA, okay? And that shouldn't be too hard to do. We'll just say return A equals, and what do we need to do here? Well, we need to wrap in a capital S constructor a function from S to A of S. S to a pair of A and S. Okay, so lambda S to A comma S. And that will do very nicely. Next we want to do bind. Bind has this type, S of A to S of B to, I'm sorry, I stuffed up slightly here. These types are slightly more complicated. S of S of B. Okay, great. Let's do this. So I'm just going to use the pattern matching syntax. S, F bound to K equals. And before we start, I'm just going to write down what the type of F and K are. So F has type S to A of S. K is type A to S of S of B. Okay. So, first thing we're going to want to do is the same thing as what we did for return. We're going to wrap it all in a big S constructor. And then it's going to be a function, so I'll do lambda S dash, and then I can get started. So the first thing I want to do is get something of type pair A comma S. So something equal, well, how are we going to do that? So what we're going to need to do is apply the F to the S, and that will give us something of type A comma S. And then we can pattern match on that, and I'm going to call these A and S prime. It's a new state. And then what we want to do eventually is produce something of this type. Yeah, okay. So, or this type here. what we really want to do is have this whole function here be of type s to b of s at the end. Because when we wrap it in this s here, that will then become this. So we really want to get a pair of b comma s at the end. Alright, so how are we going to do this? Well, what we're actually going to do is run s, k of a, s prime. Now that may not be immediately obvious why that works, so I'm going to run through that. K of a, first up. Okay. K of a has type SSB. How do we know that? From this type up here. So we applied the K to the A and we got back an SSB. Well, then what we want to do is we want to unwrap that so that it's a function. We just stick a run S in front of it. So run S of K of A, let's just clean this up a bit, is going to be of type S to B of S. Okay? And then all we have to do is apply that to S prime. So run S Ka of S prime is now going to be of type B, pair B comma S. And that is just what we want. Because now we have this lambda S here, and then the whole thing here, alright, is of type S to B comma S. And then we wrap it in this S, and we get the right thing. So if I save this file right now, and then reload, it should just work. Now, first thing I'm going to do is add some useful functions for the state monad. The first one we want to do is a function which will read from the state monad. So that's going to be read, it's a type S, S, and what's the return type going to be? It's actually going to be S as well. So read is equal to S applied to some function which returns an S. Okay, so it's going to be lambda S dash 2 something comma S, because they all have this form, right? Well, I actually want to return the state, so it's just going to be S comma S. Okay, that should load. That's good. Next, we want to have a function which writes. So this is how we write over the state. What we're going to do is take something of type S, and then we're going to go to an S of unit. Just, we don't care about its return value, we just want to overwrite the state. So write S prime equals S dollar and then lambda S to something. What's it going to be? Well, it returns a unit value and we overwrite the old state. So that's how we write it. I suppose if I was really being pedantic, then I would actually put lambda underscore here, just to show that we really are throwing away the old state. And in fact, I could remove these primes here as well. Alright, that's nice. So now what I'm going to do is write foo, a function called foo. It's going to be of type s int int. Okay? Because I'm going to return, so the state is of type int, and the value, return value is of type int. So I'm going to do foo equals do, and then I'm going to first read from the state, and then going to write x plus 1 to the state. I'm going to read from the state again, and then finally I'm going to return x. Okay, reload, that loaded very nicely. And now I'm going to write a little test function just to test it out. So test, which is of type int comma int, it'll just run s on foo, which as we know has the type int to int comma int, because foo has type s int int. So if we just look up here, that's how we know this type should be int comma int. And then of course we have to apply it to one more thing, which is 0. So what we should expect when we run this is that we get back the pair 1, 1, because we first read from the state, and it was 0, then we wrote 1 into the state, then we read from the state again, then we returned 1 as the return value. Actually, I'm just going to change this slightly and put x plus 3 here so it's a bit more interesting. So this should actually return 4, 1. Let's run it. 4, 1. Beautiful. The first bit is the return value, and the second bit is the state. Cool. So what I'm going to do right now is run through a sample evaluation in the comments section. But first, what I'm going to do is I'm going to pretend that I don't have to wrap this function in this special constructor. I'm going to pretend that I can write an instance for the monad on just the function type. So this is not actually possible, but it will simplify the presentation. So instance monad, and what I'm going to put here is lambda s2, I'll just use an underscore s. This isn't real Haskell syntax, but what I'm trying to say here is, what would it look like if we could write the monad instance just on that? Okay, so I'm going to pretend that now really return has type A to S to A comma S. I think this is just a little bit simpler. We have up here a lot of wrapping and unwrapping with this capital S constructor. Right, so it should equal lambda S to A comma S. And then bind is going to have quite the type. It's going to be S to A comma S. Probably going to make a mistake here, but hopefully you'll get the gist. A to S2 B comma S and to S2 B comma S. I hope that's right. Anyway, then F bound to K would equal, and this is going to be very similar to the previous one. It's just going to be lambda S to let A comma S prime equal F of S in, and we don't need the run S now, so it's just going to be K A S prime. I think that's quite simple. So that there is meant to be equivalent to this. Alright, now I'm going to write read again. So read S, read equals lambda S to S comma S, and I can kind of rewrite that like this. It might be a bit nicer. And then write S prime is equal to lambda underscore 2 that. Okay. And I guess if I really, really wanted to, I could write it as this. But for now, I'm not going to do that. So now what I'm going to do is rewrite foo above in the non-do notation. So that looks like this. So keep your eyes on that. I'm going to do foo, read bound to lambda x, and then write x plus 1 bound to lambda, I don't care, to read lambda x down to return x. Okay. And if I were to rewrite that in one line, it would look like this. Alright, so now what we're going to do is run through a sample evaluation of test. Test was equal to run s foo0. Here it's just equal to foo0 in our simplified presentation. And now I'm going to rely on referential transparency to replace foo with the body. And here's one I prepared earlier, but I didn't actually use x plus 3. So I'm going to put that in there. So that's what I wrote above. Yeah, this wasn't right too. Let's make the x plus 3. Okay. Just a moment while I plug in my power cord, because I'm going to run out of battery in a second. Okay, cool. Now let's get to work. So the first thing I'm going to do is evaluate this bind, okay? Because our definition for bind is up here. So this is all stuff I prepared earlier, but I'm going to have to change it slightly. Alright. So that looks like this. So all I've done is I've substituted in read here, the F, and I've substituted in all this, the K up here. And of course, that's meant to be x plus 3. Alright, cool. So the first thing we want to do, probably, is just apply it to this 0. So I'm going to get rid of this lambda s and then substitute everything in. So I should get something like this. Well, we can just do this manually. So that's going to be 0. Wow, we really didn't get rid of much there at all. Okay. And then we know from the definition of read that that's going to just return 0, 0. So that's pretty much the same line as before, except now I've replaced read 0 with 0, 0. Let's move that over. That's looking good. And then we can get rid of this let. And so now we should just get this, where A and S prime have been both replaced with 0 and 0. That's good. Right, and then what we can do is apply this to this, and we will get right 0 plus 1. It's of course going to be x plus 3 again. Okay, so we've got quite far along so far. Now we need to expand out bind again. So we're going to get this. Look at what the definition of right is. Actually, I should really put that into a lambda underscore. 1 is just equal to 0 plus 1. I'm still applying this whole thing to 0. Alright, we haven't quite got there yet. So all I've done is expand right to that. I didn't actually expand out bind in this one, sorry for lying. Alright, now we will expand out bind, and we're going to get something like this. Again, sorry, x plus 3. Boom. Alright. What shall we do next? The first thing we should do is apply this S here, this 0 here. So we're going to get this. I've simply replaced the S with a 0. And then the next step, I'm just really doing one thing at a time here. The next step is going to be this. All I've done is applied this to that to get this. Which will give us, actually let me just do this manually now. I'm sure I can do this on the fly. So the A and the S prime have been replaced with unit and 1. I don't need that trailing bracket there. So we're getting really close now. So now we apply this lambda underscore to the unit, and we're just going to get this close to 1. Getting really, really close now. Now we're going to have to expand out the lambda again. So that's going to be lambda s, let a comma s prime equal read s in lambda x return x a s prime, all applied to 1. Now we apply the lambda s to 1, and you get let a comma s prime equal read 1 in lambda x to return x s prime. And then finally, we have let a comma s equal 1 comma 1, because that's what read does. Remember the definition up here. In lambda x return x as prime. Finally, substituting for the a and the s prime, you're going to get lambda x return x applied to 1 and 1. And I'm very, very sorry, it is x plus 3, it has been the whole time. Knew that was going to happen. Just going to forget about it. And then we'll apply this first lambda to the first argument, and we'll get return x plus 3 and 1, and then finally we just do this. So we know that return is really this. Apply that to 1, and then finally we apply that lambda. Sorry, that's meant to be 1 plus 3 there, which we know to be 4. And then we finally apply this, and we get 4 comma 1, which is as our result. So there you go. I hope that that has elucidated how the state monad is actually threading through these values each time. And I hope, in conjunction with the comments that I made this afternoon, that the state monad makes a lot more sense than it did at the end of today's session. Alright, I'll see you at the next session.